like energy diagrams because they illustrate how the energy changes during the progress of a reaction. Now we're going to draw generic energy diagrams, one for an endothermic reaction and one for an exothermic reaction, and talk about some of the things that we can see, like why is delta H positive or negative, or what is the activation energy, and what's the difference between having high activation energy and low activation energy. So let's start by drawing the energy diagrams, and I'll kind of talk you through how I think about them. And then on the next slide, we'll kind of make a list of the ideas that we can take away from our energy diagrams. So I'm going to have to draw two of them, and I like drawing them side by side. So we have an endothermic reaction, and the definition in endothermic, we're going to have the energy or the heat absorbed. And then we also have exothermic reactions, and this is the case where the energy or the heat is released. Now the energy diagram is like a quadrant. It's a quadrant in a graph, so it's going to have two axes. The coordinate. Okay, and so along the x-axis, this is the progress of the reaction. You could think of it as time, or the beginning of the reaction to the end of the reaction. And then on the y-axis, so it's going this way, and on the y-axis we have energy. And so as you go up, you get higher in energy, and both axes are this way. So I'll write two of them. Now remember, we're going to start out, and our reactants are going to have some energy. Now, energy in a chemical that has potential energy that's stored in the bonds. So the energy of our reactants is never going to be down at zero. It's going to be above zero somewhere. Now, since these diagrams are generic, we are just going to kind of pick random spots. So I'm going to draw on this diagram for endothermic. I'm just going to draw here a line, and that represents the energy of my reactants. And I'll just put ER there. The R stands for reactants. And my exothermic, just so you don't think they would have to be the same, I'll start with my energy of my reactants here. So every reaction has energy. The reactants have a certain amount of potential energy that are stored inside the chemical. So you start with your reactants, and as you go through the progress of the reaction, you're going to make your product. So in an endothermic reaction, energy is absorbed. So thinking about energy being absorbed, if you start with a certain amount of energy and you absorb more energy, then when you end, you're going to have more energy than you began with. So my products for my endothermic reaction, the energy of my products is going to be higher than the energy of my reactants. And I'm going to write E with a little p for energy of my products. So again, because endothermic reactions absorb energy through the process of the reaction, the energy of the products end up being higher than the energy of the reactants. Now, an exothermic reaction, that releases energy, so the products should be lower than the reactants. And I kind of started my reactants kind of low, which makes my products even lower. And again, it doesn't matter if you started higher, that would be fine. The important thing in exothermic, since you're releasing energy, you need to be sure that the energy of your products is lower than the energy of your reactants. I think maybe for the future, for some of the labeling I'm going to do, I'm going to reorient my energy of my reactants to be higher. That better shows you in exothermic that you're releasing energy and the energy has to be lower. Okay, so I think of energy diagrams kind of like a trip. And so remember, for a reaction, we were talking a little bit about a collision theory, that in order for a reaction to occur, when the reactants collide, there has to be two things. They have to have enough energy, and then they have to have a favorable orientation. Now, to have enough energy, why would they need energy? Because it takes energy to break the bonds. So what we see is to break the bonds, the energy goes up, you need more energy, and then when you make bonds or form bonds, you release energy, so it comes back down. So you have this mountain, and this is a little exaggerated, but remember, it's the effect. We're trying to get conceptually what happens. So when you have reactants, you have to put energy in that's going to cause the bonds to break. Once the bonds have broken, then they will form new bonds, and the formation of new bonds is exothermic, so it releases energy back down. Well, an exothermic reaction does something very similar. So the energy goes up as you break the bonds, and then when you make the new bonds, it goes down. So our energy diagrams look like, I kind of think of it as a trip going over a mountain. When you have an endothermic reaction, you absorb energy, so you're going to end up in the end at a higher energy than you started with, but you still have to go over this mountain. And exothermic reactions, you end up at a lower energy than you started with because energy is released, but you still have to go over this mountain. So in general, this is kind of what an energy diagram might look like. And again, mine's a little bit exaggerated. It would probably be a little smoother or flatter, but it's fine. Now, so let's label some of the things here. So I like, for when I'm thinking about labeling things, right where the energy of the reactants start, I'm going to draw this little blue line. It's not really part of the graph, but it lets me know where I started. It's the starting point, and I'm going to do that here because some of the things we're going to label are from that starting point, and this lets me see the starting point throughout the whole graph. Now the first thing I want to label is called the activation energy. Activation energy is going to be the difference between where the reactants start and up here at the top, which is called the transition state, and I'll label that in a minute. So the amount of energy it takes to get to the top of the peak is called the activation energy. It could also be written as E with a lowercase a. So it's from the top of the peak here and from where you started. That amount of energy is the minimum amount of energy that you need for this reaction to proceed. And the higher the activation energy, the slower the reaction. Okay, so the more energy you have, the slower it takes, or the longer it takes to get from the reactants to products, or the reaction is very slow. When the energy of the activation energy is very low, a lot of molecules are going to have enough energy to go over it, and the reaction ends up being very fast. Now the definition of the activation energy would be the same here. In the exothermic, it's from the energy that you started with in your reactants to the top of the peak. Now at the top of this peak, we call this spot here, the top, the transition state. The transition state, I kind of think of it as an in between the reactants and the products. So think of the word transition. So transition means you're changing from one thing to another. This is a theoretical point where the bonds are getting ready to be broken and the new bonds are getting ready to be formed, and you're in between the reactants and the products. And it again would be at the top of the peak here. The highest energy is where the transition state would be. Now another thing we can begin to understand on these diagrams is the energy of the reaction. Now the energy of the reaction, or delta H, is the difference between the reactant's energy and the product's energy. So it's the difference from where we started and where we finished. This is delta H. Okay, so delta H, or the energy or heat of the reaction, also known as enthalpy, is equal to, you take the energy of the products, not reactants, the energy of the products, and subtract the energy of the reactants. So looking here at endothermic, the energy of the products up here is a bigger number than the energy of the reactants down here. So if we subtract a bigger number minus a smaller number, we'll have a positive value. So when we say that an endothermic reaction has a positive value, it's because the energy of the products are higher than the energy of the reactants. So when we subtract those two numbers, we get a higher value. Now let's take a look at the exothermic reaction. So again, delta H is equal to the energy of the products, the final where we finish, minus the energy of the reactants. Okay, so that means I'm taking this number down here, and subtracting this number up here. So if you take a smaller thing and subtract a larger number, then you get a negative value. So this difference right here is delta H, and it would be a negative value for exothermic because the energy of the products is lower than the energy of the reactants. So this kind of lets us know, and we can see how positive values go for delta H go with endothermic and negative values go with exothermic. Now the sign of delta H will determine whether the products or the reactants are lower in energy, and reactions are favored where delta H is negative. So reactions are favored for exothermic reactions. Remember, in chemistry, the lower in potential energy you go, the more stable you are. So let's kind of summarize a few of these things about the reactions and some of the things that we can refer back to. So endothermic reactions, we know by the definition that heat is absorbed. We know that the energy of the products is greater than the energy of the reactants because the heat is absorbed. We determined that then, if the products is greater than the reactants, we have a positive value. Instead of writing value, I think I'm just going to write a positive delta H. So the number would be positive, have a positive sign. Okay, exothermic reactions. So heat is released, that's the definition. And because the heat is released, then the energy of the reactants is greater than the energy of the products. The reactants are higher than the products. And because of that, when we subtract the smaller products from minus the reactants, we have a negative value of delta H. Now, if you remember that the one thing we talked about in class is that the lower the energy, the more stable and the stronger the bonds. So in an endothermic reaction, since the reactants are lower, they would have a stronger bond. And in an exothermic reaction, the products are lower, so the products have a stronger bond. Oops, I forgot to write bond. I got ahead of myself. Now, one thing that we also looked at the graph was the activation energy, or EA. Now, EA does not affect, what EA does affect, the activation energy affects how fast the reaction is. So a higher activation energy, the slower the reaction. And the lower the activation energy, the faster the reaction. Well, I think that's a pretty good start for getting a summary on what energy diagrams can tell us and how they relate to some of the things that concepts and things that we memorize and learn about. This is a nice illustration to maybe, especially for some of you, tie that into what we're learning.